Good evening, students. Welcome back. Welcome to day 12 POC-II crash course. In today's session, I'll be starting unit 4. So I'll be discussing about chemistry of naphthalene. In yesterday's session, I have discussed about stability theories of cycloalkane, where I explained about base strain theory along with its limitations, Coulson-Moffat's theory or modification, and also Sachet-Moore theory. Few very important examination questions. Okay, in fact, they are the definite questions. Just earlier session, then a replay will be available in my YouTube channel. You can watch it. From time to time, you can post your doubts in the live session. Alternatively, if you are watching the replay of this particular session, then a WhatsApp group link will be available in the description. You can join in that WhatsApp group and you can clarify your doubts at later stage. And soon after this particular session, quiz will be enabled. Okay, so review the concept for about 10 to 15 minutes. As soon as this session is completed, then only attempt the quiz. Now, in this particular session, I'll be explaining about the isomerism, resonance phenomena, and the methods of preparation, reactions, and uses of naphthalene and its derivatives. Now, without wasting much of your time, let us jump into today's topic. This is the structure of naphthalene. So naphthalene consists of two benzene rings fused linearly. Okay, so this is called linear fusion or ortho fusion. That means side by side both the aromatic ring systems are fused. So two benzene rings are fused with each other. You can see there are 4 this side and 4 this side isolated carbon atoms are there. And these two ring systems are shared via 2 carbons. Okay, so 4 plus 2 plus 4. Overall 10 carbons are there. Now, junctional carbons, they do not possess any hydrogen, while the rest all carbon atoms, these 8 carbon atoms are having hydrogens like benzene structure. So, there are overall 8 hydrogens are there. So, that is why the molecular formula of naphthalene is C10H8. The major source for naphthalene is coal tar and petroleum. So, these organic reservoirs are subjected for fractional distillation, and in one of the fraction, upon further purification, we will be getting naphthalene. So the structure of naphthalene is also similar to that of benzene. The difference is benzene ring system, it consists of only one aromatic ring system, while naphthalene, it consists of 2 aromatic ring systems. So whenever such type of systems are present, those molecules will be exhibiting resonance phenomena. So it is because of this reason, even naphthalene is having resonance phenomena, and thus it is aromatic in nature. Now, when it comes to polynuclear aromatic hydrocarbons, in generally, the number of resonance structures, it depends on the number of aromatic rings present in the given molecule. Each polynuclear aromatic hydrocarbon, it consists of n plus 1 number of resonance structures. So here n is nothing but number of rings. So if you consider naphthalene as an example, naphthalene consists of 2 aromatic ring systems. So 2, that means here n equals to 2. So 2 plus 1 means 3. That means the total number of resonance structures possible for naphthalene are 3. So these are the 3 resonance structures for naphthalene and its corresponding resonance hybrid. Now let us see how these 3 resonance structures are written. So for simplification purpose, we have numbered these benzene ring system as 1 and 2. Okay. On the other hand, you can also number these benzene ring systems as A and B ring systems also. So in the first resonance structure, the first benzene ring system, we have written similar to benzene structure. Okay. Now coming to the second benzene ring system, because naphthalene is an aromatic compound and having resonance phenomena, we will be keeping double bonds at alternative positions. That means all double bonds which are present in naphthalene are in conjugation with each other. Because already junctional carbon atoms are doubly bonded carbon atoms, now we will leave one bond here, okay, and then at other position we'll keep double bond. So that is how we have to adjust the double bond in the second ring of the first resonance structure. So this is how we can draw first resonance structure of the naphthalene. So the first ring we have written another Kekulé structure. That is the only difference, okay. So the other 2 double bonds in the second ring in second structure are also similar as that of the first. Only we have changed the position of double bonds in the first ring. That is the only difference between the first and 2 resonance structures. Okay. Now coming to the third resonance structure, how it is drawn. So far we were first writing the Kekulé resonance structures of benzene with respect to the first ring. Okay. Instead, now for second ring, the one of the Kekulé structure of benzene was given first. Okay. Now accordingly adjust the double bonds in the first ring system, because these junctional carbon atoms are already having double bonds as per the Kekulé structure in case of ring 2. Now the adjacent positions we have to leave. Okay, we should not keep any double bond, so that we will left over with only these two positions to keep the double bond. So that is how two double bonds should be adjusted with respect to the first ring system. Okay, so this is how, just by what is the meaning of resonance structures, as you are already aware, that resonance structures will differ in arrangement of electrons. Molecular formula will be similar only. Okay, they differ only in terms of arrangement of the electrons. So this is how we can make three resonance structures for naphthalene. Okay. Now, if you combine the structural features of all these three resonance structures, okay, so first write two hexagon ring systems, combine all these three resonance structures, you can easily make out that all the 10 carbons in benzene are having double bond character. So to represent that, a circle is drawn near to the hexagon structures with respect to both the ring systems, and this is how we will draw resonance hybrid structure. Okay, so the original structure of naphthalene is the resonance hybrid structure. Okay, so the total number of aromatic rings in naphthalene are 2. So 2 plus 1, that means 3 resonance structures are possible for naphthalene, and this is how we will draw the 3 resonance structures and the resonance hybrid structure for the naphthalene. You have already learned in case of benzene that compounds which are exhibiting resonance phenomena will be stable. Now let us compare the stability of naphthalene versus benzene. Naphthalene, so the structures of benzene and naphthalene are given here. And the benzene resonance energy, you are aware, it is 150.6 kilojoules per mole. Benzene is having only one aromatic ring system. Coming to naphthalene, resonance energy of the naphthalene is 255.2 kilojoules per mole. Okay, while naphthalene, it is having two aromatic ring systems. Okay, now in order to compare the stability, we have to compare a common property. So benzene is having only one aromatic ring system, while naphthalene is having two aromatic ring systems. Naphthalene resonance energy when it is having two aromatic ring systems is 255.2 kilojoules. Now with respect to each aromatic ring system, we have to calculate the naphthalene resonance energy. So in that case, we have to do divided by 2. That means 255.2 divided by 2. Then we will get around 127.6 kilojoules per mole. Okay, that means naphthalene resonance energy with respect to each benzene ring will be around 127.6 kilojoules per mole. When you compare this value with the benzene resonance energy, so naphthalene resonance energy is less when compared with benzene. Okay, so here aromaticity is proportional to the resonance energy. Okay, so lesser the resonance energy, lesser will be the aromaticity, and hence lesser will be the stability. So that is why naphthalene is less aromatic than benzene, and hence it is more reactive. And stability wise, if you see, benzene is more aromatic than naphthalene. That means benzene is more stable when compared with naphthalene. On the other hand, you can say naphthalene is less stable when compared with benzene. So I hope the resonance phenomena and the resonance structures of naphthalene is clear to you from the earlier discussion. So if you have any doubts, you can keep your doubts in the chat. So this next topic which I am going to take is the isomerism in naphthalene. Let me share my screen to take up isomerism in naphthalene, because this particular concept will be help you to identify the preferred point of attack when it comes to the electrophilic substitution reactions of naphthalene. So here the structure of naphthalene are given. Both are naphthalene structures only. But what is the difference is, here two types of nomenclature generally we will be giving for the positioning of naphthalene ring system. As you are aware that total 10 positions are there. That means 10 carbons are there in the structure of naphthalene. These carbon atoms are known as junctional carbon atoms. And in all these polynuclear aromatic hydrocarbons, we don't give numbering to the junctional carbon atoms. Okay, if you look at the first structure, so I have given alpha beta nomenclature. Okay, so here two different positions are existing in the structure of naphthalene, and these two positions are differentiated as alpha position and beta position. So let us first consider alpha position. Okay, now the pointed position, alpha position, if you see, one side it is having 1, 2, 3 carbon atoms, okay, within the same ring system. Now other side it is having fused with benzene ring system. Okay, let us say with these features it is alpha position. Now look at the other alpha position, this highlighted alpha position. Okay, it is also having 1, 2, 3 carbon atoms in its own ring system. Other side it is having 4 carbons which are present in the benzene ring system. Okay, that means the chemical environment around this alpha carbon and this alpha carbon are identical. Similarly, look at the alpha position which is highlighted in the next ring system. So with respect to this position, if you see, this alpha carbon is adjacent to 1, 2, 3 carbon atoms in its own system, and remaining and other side it is attached to benzene ring system. And even with respect to the last alpha carbon, which is present in the second ring system also, this alpha carbon is attached to 1, 2, 3 carbon atoms in its own ring systems. Okay. And other side it is attached to the benzene ring system. Chemical environment surrounded by all these four positions is identical. Okay. That is why these four positions are considered to be identical positions and they are designated as alpha positions. Now coming to the beta position, let us consider first this beta position. Okay. Now this beta position, on one side it is attached to a single carbon which is connected to ring system, aromatic ring system, and other side it is connected to two more carbon atoms. Again it is continued with another aromatic ring system. Okay. So this is the chemical environment around this particular beta position, which is denoted as 2 in the other structure. With respect to this beta position, it is surrounded by one carbon and two more carbons on other side, and then other side it is having aromatic ring system. Okay. That means the chemical environment surrounded by this carbon and this carbon are identical. Similarly, you can consider other beta carbons, that is nothing but 6th and 7th carbon atoms also. The chemical environment surrounded by all these carbons which are denoted as beta are identical. Okay. That is why they are designated as beta positions. Okay. That means there are these four positions are identical, which are denoted as alpha carbons or alpha positions, and these four positions are identical and they are denoted as beta positions. That means overall, out of the 8 positions in the structure of naphthalene, all the 8 positions, they belongs to 2 classes. 4 are alpha positions, 4 are beta positions. Okay. Now when we say alpha, whether we are pointing out this position or this position or this position, we get confusion because there are 4 alpha positions are there. Similarly, 4 beta positions are there. So to explain it very clearly, numerical values are given. Okay. So when it comes to numbering of naphthalene will be given like this. Okay. So first we will start from right hand side aromatic ring system. Okay. So the alpha carbon is denoted as first carbon. Then 1, 2, 3, 4, 4 carbons are present in the first ring system. So when we are moving from one aromatic ring to the other aromatic ring, we will continue the number. Okay. As I mentioned, we have to omit these junctional carbon atoms. We don't number these junctional carbon atoms. So after 4, this will be the 5th carbon. Then 6, 7, 8. So total 8 positions are there. Okay. Now with respect to numbering, if you see, as I mentioned, there are 2 different positions are there in the structure of naphthalene. They are denoted as alpha position and beta position. Okay. Now what is the meaning of alpha in terms of numbers? If you see 1, 4, 5 and 8. These 4 positions are denoted as alpha positions, and remaining 4, that is 2, 3, 6 and 7 positions are denoted as beta position. Okay. Naphthalene is also aromatic compound. It will undergo electrophilic substitution reaction similar to that of benzene. So when you perform electrophilic substitution reaction for naphthalene, there will be possibility of formation of 2 isomeric products. Okay, that is alpha isomer and beta isomer. So the details of these electrophilic substitution reactions of naphthalene, anyway, I'll be discussing in the next coming course videos. So overall, if you see, naphthalene consists of 8 positions. These 8 positions are classified into 4 alpha positions and 4 beta positions. Okay, so and upon substitution, naphthalene gives 2 isomeric products. I hope the resonance phenomena and the isomerism in naphthalene is clear to you from the earlier discussion. So if you have any doubts, students, you can keep your doubts, you can post your doubts in the chat. So alternatively, if you are watching the replay of this particular session, then a WhatsApp group link will be provided in the description. You can join in that WhatsApp group and clarify your doubts. Now the next topic which I am going to take is the methods of preparation of naphthalene. Okay, so first I'll be covering one of the most important preparation, that is Haworth synthesis, because you may get this as a 2 marks question also. Okay, along with that I'll be giving one more example method of preparation for naphthalene. Synthesis is one of the named reaction by which we can prepare these polynuclear aromatic hydrocarbons. So not only naphthalene, even anthracene, phenanthrene can also be prepared by Haworth synthesis. Only the starting molecules, okay, will vary, but the type of reaction sequence will be same in all types of Haworth synthesis, whether it may be synthesis of naphthalene, anthracene or phenanthrene. Now let us discuss about Haworth synthesis of naphthalene in this particular video. So in this reaction, we are going to synthesize naphthalene. Now, what is the structure of naphthalene? Always the compound which you want to synthesize should be kept in mind. Naphthalene consists of 2 aromatic ring systems, that is 2 benzenoid ring systems fused to each other. Okay, so in order to prepare such type of molecule, here we are taking benzene as one of the reactant. Okay, and another molecule that we are taking is succinic anhydride. Okay, again 5-membered ring containing anhydride. First step is Friedel-Crafts acylation reaction between benzene and succinic anhydride in the presence of aluminum trichloride. Friedel-Crafts acylation reaction of benzene is already discussed in the earlier module. In all Friedel-Crafts reaction, aluminum trichloride is used as one of the catalysts, and because it is acylation reaction, here acyl group containing molecule is taken. Okay, so which is nothing but the acetic anhydride. Okay, so what is the acyl group in the acetic anhydride? If you see, this is CH2, CH2, CO on either side, followed by oxygen. Okay, this is the structure of acetic anhydride. So this CH2COO is nothing but the acyl group. Okay, only thing is now this acyl group is present in the cyclic ring formation. Okay, so this is also very much similar to that of the Friedel-Crafts acylation reactions of the benzene. Now, during this Friedel-Crafts acylation reaction of this cyclic molecule, cleavage occurs here. Okay, so that the carbon-oxygen bond will be broken and this carbonyl group will be attached to the aromatic ring system at this particular place. Now let us see the resulting molecule. So again write the benzene. There is no difference in the benzene structure. So write the benzene structure as it is. Now attach this CO group, carbonyl group to the benzene ring system as shown in this arrow. Okay. So now this will become, this is CO. Okay. This CO. And this CO is attached to CH2 group. So this is that CH2 group. And this CH2 group is again attached to one more CH2 group. And that is this CH2 group. Okay. And now this CH2 group is attached to COO. Okay, so this part, COO. So that COO part, because ring is undergoing cleavage at this particular position, this COO group is converted to carboxylic group. Okay, so that is how we will be getting an open chain molecule. So there is no change in this particular benzene ring system, but the succinic anhydride molecule is undergoing cleavage, and because of the ring opening, the ring carbonyl group is attached to the aromatic benzene. Okay, and finally this COO group is converted to COOH. That is how we are getting corresponding open chain molecule. So stepwise we will try to remove this CO group and then OH group should be removed so that this particular carbon attaches to the benzene ring system here. Okay, and that is how we will be getting a cyclic ring system. Okay, in order to facilitate the further formation of naphthalene ring. So now let us see, in the first attempt, we will be converting this CO group to CH2 group. Okay, so here CH2 group is there. So how to convert that? So carbonyl compounds, carbonyl groups can be converted to corresponding hydrocarbon groups by performing Clemmensen reduction. So here the resulting compound, this intermediate, is treated with zinc amalgam in the presence of HCl so that this CO group gets converted to CH2 group. Okay, so there is no change in the structure of these two compounds. Only the difference is CO is converted to CH2 group. Okay, so such type of reduction is known as Clemmensen reduction. So we don't want this OH group also. Okay, so this OH group along with hydrogen is removed in the form of water molecule by treating this particular resulting compound with concentrated sulfuric acid. Whenever we add concentrated sulfuric acid, it acts as dehydrating agent, and here hydroxyl group from carboxylic group and hydrogen from the benzene ring system from the ortho position will be removed in the form of water. So that is how dehydration reaction occurs. Dehydration results in cyclization, and during this cyclization, this carbonyl group is attached to the aromatic ring, and that is how we will get finally alpha tetralone. Now this tetralone, now the resulting compound is also still having carbonyl functionality. Naphthalene structure does not possess any carbonyl group. That means we have to convert this carbonyl group to hydrocarbon. So again, to perform that, we will be using same Clemmensen reduction here also. So again, the resulting alpha tetralone is treated with the zinc amalgam in the presence of HCl. So that this CO group will be converted to CH2 group. And that is how tetralone gets converted to tetraline. Now the difference between the final naphthalene structure and the tetraline structure, if you see, one of the benzene ring system is ready. Now coming to the other benzene ring system, 6-membered ring is present, but it is lacking the 2 more double bonds. Okay, so how we can introduce double bonds? By performing a dehydrogenation reaction. Means when you remove hydrogens from the tetraline, by removal of 4 hydrogens, 2 double bonds will be introduced. These 2 double bonds will be introduced. So to remove 4 hydrogens from these 4 carbon atoms, here carbon which is treated with palladium in the presence of selenium are used. So by heating this particular chemical compound, finally tetraline gives naphthalene. That is how finally, after synthesis of benzene and succinic anhydride, we will be getting naphthalene. So overall, if you see students, here the first step is Friedel-Crafts acylation reaction. Second step is Clemmensen reduction. Third step is dehydration, and fourth step is again Clemmensen reduction. Fifth step is dehydrogenation. On the other hand, students, if you feel difficulty in learning all the 5 steps, okay, just to get 1 or 2 marks when the question comes. In that case also, you can still attempt Haworth synthesis even though you feel it difficult. Okay, so how? You can just simply write like a single step reaction. So what is the first step? First step involves Friedel-Crafts acylation reaction between benzene and succinic anhydride in the presence of aluminum trichloride. So you give that clearly and then keep multiple arrows. So whenever we keep multiple arrows like this, it indicates that this reaction involves multi-step. It is a multi-step reaction. Okay. So we are not mentioning individually what are those steps. Okay. Upon this multi-step reaction, finally we will get naphthalene. If you are feeling difficulty in writing the whole mechanism involved in Haworth synthesis like this, then you can also show in a single line like this. Okay. Now again, one more method of preparation also you can learn, which involves single step. So that is from 4-phenyl 1-butene. And you can number the carbon chain like this. 1, 2, 3, 4 carbon atoms are there. At first position, double bond is there. That means it is 1-butene. Now this 1-butene is having phenyl group. This is phenyl group at 4th carbon atom, attached to the 4th carbon atom. That is why it is named as 4-phenyl 1-butene. So when we subject this 4-phenyl 1-butene to red hot calcium oxide, here cyclization occurs and then followed by removal of hydrogens from these carbon atoms, 3 and 4 carbon atoms. So already at 1 and 2 double bond is there in the butene structure itself. Now upon dehydrogenation at 3 and 4 also double bond will be introduced. So that is how cyclization followed by dehydrogenation occurs, and as a result of which finally we will be getting naphthalene. So I hope Haworth synthesis of naphthalene is clear to you, students. So if you feel difficulty in writing all the 5 steps, then you can write it as at least a single step, that is multi-step. You will be keeping multiple arrows and you will be representing as a single step reaction, so that at least you can, if the question comes for 5 marks, at least you can score 2 marks. And if the question comes for 2 marks, you can score at least 1 mark. Okay, so in that way also, don't skip the questions, learn everything, but learn very briefly. In that way you can score maximum marks. Now that you have understood about the Haworth synthesis and the other method of preparation of naphthalene, now let us consider what type of reactions naphthalene will undergo, and also let us first begin with the electrophilic substitution reactions of the naphthalene. Let me share my screen to explain the same. This is the structure of naphthalene. Any compound, it undergoes reaction depending on its structure. Here, as you have seen here, naphthalene consists of 5 double bonds. Compounds which are having double bonds are considered to be electron-rich sources, and that is why they will undergo electrophilic substitution reactions. So naphthalene also undergoes electrophilic substitution reactions due to the presence of aromatic rings similar to benzene. Now the other type of reactions are addition reactions. It is because naphthalene consists of 2 aromatic ring system. If the addition occurs with respect to one benzene ring system also, the aromaticity of the second benzene ring system will be maintained as it is. That means the aromaticity will be preserved. As a result of which, naphthalene upon addition reaction, still it gives corresponding aromatic compounds. It is because of that reason naphthalene undergoes addition reactions. Now, due to the presence of double bonds in the structure of naphthalene, it will undergo both oxidation as well as reduction reactions. Now, let us first consider the electrophilic substitution reactions of naphthalene in this particular course video. Why only electrophiles are the preferred attacking groups on the naphthalene, and why only substitution occurs? This is similar to the explanation which I mentioned in case of benzene. So due to the availability of 5 pi bonds in the structure of naphthalene, naphthalene is considered as one of the electron-rich molecule. Because it is electron-rich species, it attracts the electron deficient species. So the electron deficient species are known as electrophiles. So due to the availability of pi bonds in the structure of naphthalene, it becomes center for the attack of the electrophiles. Now, what is the reason why naphthalene prefers electrophilic substitution reactions? If you see, in a substitution reaction, one group will be replaced with another group. So, upon replacement of the group, yet the naphthalene ring system, it preserves aromaticity. It is because of this reason, naphthalene undergoes electrophilic substitution reaction similar to that of benzene. As we have discussed in case of benzene, the electrophilic substitution reactions of any aromatic compounds, it involves 3 steps. So the mechanism involved in electrophilic substitution reactions of naphthalene is also similar to that of benzene, involving the same 3 steps. But in case of benzene, all the 6 hydrogens which are present in the structure of benzene are chemically equivalent. So upon replacement of any of these 6 hydrogens, we will be getting same monosubstituted benzene derivative. But in case of naphthalene, as I have discussed under isomerism in naphthalene, Because naphthalene consists of two different types of hydrogens, that is alpha hydrogens and beta hydrogens. The incoming electrophile, whether it attacks at alpha position or beta position, that is a big question. Okay, so what is the preferred point of attack of electrophile on the naphthalene ring system, whether it is alpha position or beta position? So in order to get answer for this, we have to first think about the rate determining step. Okay, the rate determining step in electrophilic substitution reaction is the formation of carbocation. So in these reactions, stability of resulting carbocation is very important. So whether the preferred point of attack is at alpha position or beta position, it depends on the stability of the formed carbocation in the rate determining step of the electrophilic substitution reactions of naphthalene. So we have to write the rate determining step, which is nothing but the carbocation formation for the electrophilic substitution reactions of naphthalene. Okay, for both the positions, alpha position as well as beta position. So pause this video here because you already learned about the electrophilic substitution reaction of benzene along with its stepwise mechanism. Try to write the electrophilic substitution reaction for the naphthalene at both the positions, alpha position and beta position. Okay, now look at the resulting carbocation structure. Okay, so how many resonance structures are possible for each alpha attack and beta attack? If you have already written, just observe the resulting resonance structures. I hope you have tried a little bit. Now I'm going to give it elaborately. Okay, so here the structure of naphthalene is taken. That means two different types of hydrogens are available. Okay, so upon replacement of each hydrogen, we can write one particular mechanism. So that's why here two attacks are shown separately, alpha attack and beta attack separately. Now let us first consider the alpha attack. That means this position, this is alpha position hydrogen. Consider Y plus as the electrophile. If Y plus attacks on alpha carbon atom on the naphthalene ring system, then at that particular position already hydrogen is available. Now by utilizing this pi bond which is available in the naphthalene ring system, Y, that is electrophile, is making a bond at first position. Okay. Now in that case the second position becomes electron deficient. That is why the second carbon bears positive charge. Okay. Write the remaining naphthalene structure as it is. We are not disturbing this particular ring system and this double bond is kept the same as that of the naphthalene ring system. Okay. Now the resulting structure has one more resonance structure because at second position the structure is bearing positive charge. To remove the positive charge from the second position, here the double bond which is present at the third position can be shifted. So in that case we will be getting a new resonance structure. Okay, so upon shifting of double bond from third position to 2, so here a new double bond is obtained at second position. Now because at fourth position, now the resulting molecule is having deficient of electrons. So that is why positive sign is shown at fourth carbon atom. That means what is happening? Just a mutual shift between the double bond and positive charge. So that we will be getting the next resonance structure. Okay, wherever the electrophilic attack is happening only on that particular benzene ring, that means in this particular benzene ring, there is loss of pi bond because those pi electrons are given to the electrophile to make a bond with the ring carbon atom. Okay, so there is loss of aromaticity in the aromatic ring wherever the attack is happening. Okay, while the other aromatic ring aromaticity is preserved. So if you look at these two structures here, for benzene ring, one of the K-class structure is represented. We know that benzene has two K-class structures. Okay, so this particular ring system where aromaticity is preserved, we can represent by using another K-class structure of benzene also, like this. Okay, so in that way, these two structures can be giving rise to two more structures. Now, the difference between the first two structures and the latter two structures, if you see, if you consider this particular benzene ring as one of the K-class resonance structure, now here, this particular benzene ring belongs to the another K-class structure. Okay, so that is the only difference. Okay, we have just moved the double bond positions. Okay, we have not disturbed on the ring where the substitution is occurring. Okay, so this second ring was mentioned same. Okay, so that is the only difference. Okay, so we get initially two resonance structures, first two resonance structures. Just by writing one more K-class structure for benzene ring, we will get two more structures. So overall, on alpha attack of electrophile on naphthalene ring system at alpha position, we will be getting 4 resonance structures for the resulting carbocation. Now, as soon as the carbocation is formed in the third step, deprotonation occurs. Immediately, we get corresponding substituted product. And that is how we will be getting one substituted naphthalene. Okay. And similar lines, if you consider beta attack. So, upon beta attack, that means this is the beta position. Okay. So, we are now considering this position. This is beta position. When electrophile attacks at beta position, then it will utilize this particular double bond only. So, hydrogen is already present at beta position also. Why? That is electrophile is attached to beta position by utilizing this particular double bond. Then the first carbon will become electron deficient. That is why it gets positive charge. Okay. While the other benzene ring system and the other double bond is kept as it is as that of the naphthalene ring system. Okay. Now from this we can draw one more resonance structure also. If you look at this structure, we cannot shift the double bond because at the adjacent position, the adjacent carbon is already tetravalent. That is why we cannot shift the double bond in the same ring system to give them one more resonance structures like as we have done in case of alpha attack. That is not possible. But alternatively, what we can do is the first ring here, one of the K-class structure is mentioned. No, for the same ring, we can mention the another K-class structure. If you see these two structures, wherever arrows are given, okay, these are the benzene rings representing two K-class structures. That is how we can just write the another K-class structure for representing benzene ring. Okay, while the other ring, wherever the substitution has been occurred, that will be remaining same. There is no difference between these two ring system. They remained same. Okay, so this is how on beta attack of electrophile on the naphthalene ring system, we get a carbocation which is having only two resonance structures. Okay, now this particular carbocation also, once it is formed, immediately it will undergo deprotonation to give the two substituted product. Now, out of these two substitutions, which substitution is preferred if you see? In case of alpha attack, the resulting carbocation has 4 resonance structures. Okay. While in case of beta attack, the resulting carbocation has only 2 structures. That means on alpha attack, we are getting more number of resonance structures when compared with the beta attack. Okay. Greater the number of resonance structures, greater will be the stability of the resulting carbocation. Because of that reason, the carbocation which is formed in alpha attack is more stable. Highly stable carbocations will be formed easily. So as soon as this carbocation is formed, immediately it will undergo deprotonation and it gives corresponding one substituted product. It is because of this reason alpha attack is preferred in case of naphthalene. So the same thing is given here in alpha or 1 substitution, resonance structures are 4. Okay. Whereas in beta, we have seen only the resulting carbocation has only 2 resonance structures. So here the thing is greater the number of resonance structures, greater will be the stability. Hence, the carbocation which is formed in alpha attack or 1 attack is more stable when compared with beta attack. Hence, electrophile prefers to attack at alpha position on the naphthalene ring system. It doesn't mean that beta attack is not possible when all alpha positions are occupied with the electrophile. Okay, there are 4 alpha positions are there in the structure of naphthalene. No, when all these alpha positions are occupied, the resulting molecule, when we perform electrophilic substitution reaction, then the next incoming electrophile prefers to attack at the beta position. Okay, that is how even beta attack is also possible. So from this overall discussion, we can understand there is 2 possibilities are there for the electrophilic attack on naphthalene, alpha position and beta position. Okay, in the alpha position, whenever electrophile attacks, the resulting carbocation has 4 number of resonance structures. Okay, that means it results in more number of resonance structures. While in case of beta attack, only 2 resonance structures are there. That means less number of resonance structures are obtained. Okay, greater the number of resonance structures, greater will be the stability of the formed carbocation. That is why as soon as the carbocation is formed, immediately it reacts, that is, it undergoes deprotonation and forms one substituted product. And it is because of that reason alpha attack is preferred in case of naphthalene rather than beta attack. Dear students, if you feel difficulty in writing these resonance structures, now you learned that alpha attack is preferred. So instead of writing all these structures, just mention here that carbocation is formed which is having more number of resonance structures. And in beta attack also carbocation will be formed which is having less number of resonance structures. Okay. And then immediately state this point which is highlighted in red is important. Greater the number of resonance structures, greater will be the stability. That is why in alpha attack, resulting carbocation is more stable. Hence, electrophile prefers to attack at alpha position. Okay. So if you feel difficulty in writing all the resonance structures, at least write in this way also. Okay. Whatever I mentioned in this slide, in that way also you can score good marks. Now that you have learned why alpha position is preferred in case of naphthalene, let us consider a few examples. So here are few examples for electrophilic substitution reactions of naphthalene. So here the structure of naphthalene is given. The first reaction, as you are aware, by looking at the reagent itself, you can easily make out this is nitration reaction. Okay, so where combination of concentrated nitric acid and sulfuric acid are used. So here, as you are aware, nitronium ion will be generated, and once nitronium ion generates, because the preferred point of attack is alpha, it attacks at alpha position. That's why we get here 1-nitronaphthalene as the product. Okay, so you can write the names as 1 or alpha also. Okay, so it is when the attack attacks on the other benzene ring system also, again we have to mention it as alpha. So that will be little confusing. That is why here I have given the numbers, but alternatively you can use alpha beta terminology also. Now the resulting 1-nitronaphthalene, if you further perform nitration, okay, then the nitration occurs in the other aromatic ring system. Okay, so the other aromatic ring system, again 2 alpha positions will be there. So that is the reason one of the product at 5th position nitro group will be attacked. In another product at 8th position, which is also alpha position, okay, nitro group will be attacked. So that's why we will be getting here 1,5 dinitronaphthalene and 1,8 dinitronaphthalene. Okay, so this is upon subsequent nitration of the resulting 1-nitro derivative. Okay. Now the halogenation reactions are little unpredictable. For example, upon bromination in the presence of glacial acetic acid, the bromonium ion attacks at alpha position, as a result of which we will be getting 1-bromonaphthalene. But the same chlorination reaction is performed in the presence of a catalyst, then all the positions, both alpha and beta positions, hydrogens will be occupied, and all the 8 positions will be occupied with chlorine. Okay, and as a result of which we get octachloronaphthalene as the product. So 8 chlorines are substituted, that's why it is known as octachloro. So another reaction is known as chloromethylation reaction. So this reaction occurs in the presence of formaldehyde, concentrated HCl and phosphoric acid. When these chemicals are treated with naphthalene, then from this formaldehyde CH2 group, okay, will be taken, and from HCl will be taken. So the CH2Cl group will be attacked at alpha position, because the preferred point of attack is at alpha. Okay, so that's why here we will be we have attached CH2Cl group to the first position. Okay, and that is how we will be getting 1-chloromethylnaphthalene as the product. So if you could not remember the remaining, that is continuation reaction, at least you try to remember up to these reactions. That is more than enough, students. I hope the preferred point of electrophilic attack on naphthalene is clear to you. So there is two possibilities will be there. The incoming electrophile can attack on alpha position or beta position, but from the resonance structures we could able to understand that alpha attack is preferred. And also we have considered some of the examples for the electrophilic substitution reactions. Now that you have understood about the electrophilic substitution reactions, let us now move to the other reactions of naphthalene, that is nothing but the addition reactions, oxidation and reduction reactions. Okay, so I'll be sharing my screen. Meanwhile, if you have any doubts related to the electrophilic substitution reactions of naphthalene, you can keep your questions or queries in the chat. Now let us consider these reactions one by one. So first let us consider addition reactions of naphthalene. So here 3 model addition reactions were given. The first reaction is addition of chlorine. So the structure of naphthalene is given. Upon addition of chlorine in the presence of light, in the first step, chlorine will be attached to 1 and 4 positions on the naphthalene ring system. And that is how we will be getting 1,4 dichloro-dihydronaphthalene. Now, when the resulting compound is further substituted for chlorination in the presence of light, now the chlorine in the next step, it attaches to 2nd and 3rd positions also. So, as a result of which we will be getting 1, 2, 3, 4. At 4 positions, chlorines are attached. So, that's why it is known as 1, 2, 3, 4 tetrachloro-tetrahydronaphthalene. Now, the next example reaction is addition of sodium. So when naphthalene is allowed to react with the sodium, here also sodium attacks at 1,4 positions in the first step, and thus results in the formation of 1,4 disodium dihydronaphthalene. The resulting compound is allowed to react with 2 moles of carbon dioxide. Then it results in the formation of disodium salt of 1,4 dihydronaphthalene, 1,4 dicarboxylic acid. So you can see here sodium salt of carboxylic acid group, that is COONA group, is incorporated at 1 and 4 positions. So that is denoted like this: disodium salt of 1,4 dihydronaphthalene, 1,4 dicarboxylic acid. Now these are the 2 addition reactions of naphthalene, chlorine and sodium. Now the third addition reaction is addition of ozone, which is also known as ozonolysis. When naphthalene is subjected for ozonolysis, so it reacts with 2 moles of ozone. So the 2 double bonds which are present in the first ring system will be subjected for ozonolysis. In a typical ozonolysis reaction, ozone molecule will be attached wherever double bonds are present. Here, the first ring of the naphthalene will be affected during this ozonolysis process. So, the first ring, it consists of two double bonds. So, wherever double bonds are there, so there the addition of ozone has been taken up. And from ozone, this is 1, 2, 3. Three oxygens from each ozone molecule are cyclized with the aromatic ring system. And that is how we will be getting corresponding diozonide as the product. That is, we will be getting naphthalene diozonide. Now, the resulting naphthalene diozonide is subjected for hydrolysis in the presence of zinc. During this hydrolysis, both the ozonide ring systems will be undergoing cleavage, and as a result of which there will be formation of corresponding aldehyde, which is nothing but thialaldehyde. And that is how upon ozonolysis of naphthalene followed by further hydrolysis, we will be getting thialaldehyde as the product. So these are the three addition reactions of naphthalene: addition of chlorine, addition of sodium, and addition of ozone. Now let us consider about oxidation reactions of naphthalene. Naphthalene can undergo different oxidative pathways. It depends on type of oxidizing agent used and also type of medium that is used during reaction. When naphthalene is oxidized in the presence of acetic potassium hydroxide, then the first aromatic ring system, this aromatic ring system is subjected for cleavage and it is oxidized, as a result of which phthalic acid is formed as the product. On the other hand, whenever naphthalene is oxidized in the presence of alkaline potassium permanganate, here also the first aromatic ring is subjected for cleavage, and as a result of oxidation, here we get thalonic acid. Naphthalene can undergo oxidation even in the presence of concentrated sulfuric acid or a mixture containing oxygen and vanadium pentoxide. So in this oxidation pathway, naphthalene gives phthalic anhydride as the product. Upon oxidation of naphthalene in the presence of chromic oxide and glacial acetic acid mixture, 1,4-naphthaquinone will be formed as the product. So that is how different oxidative products will be formed upon oxidation of naphthalene. That depends on type of oxidizing agent used during the reaction. So these are the few model oxidative pathways of naphthalene. Now let us consider some of the reduction reactions of naphthalene. So reduction reactions also, several pathways are there. Again, it depends on the type of reducing agents and the experimental conditions implemented during reaction. So the first reaction given is reduction of naphthalene in the presence of sodium and ethanol. So in this, the first aromatic ring system containing double bond, one of the double bond will be undergoing reduction. Okay. So one of the double bond will be undergoing reduction, while the other double bond, it changes its position to 2 and 3 positions. Okay. And that is how finally hydrogens will be added during this hydrogenation or reduction process at 1 and 4 positions. And that is how finally we get 1,4-dihydronaphthalene as the product. Now the second reaction is reduction of naphthalene by passing 2 moles of hydrogen in the presence of nickel and heat. That means naphthalene will be heated in the presence of nickel by passing 2 moles of hydrogen. So because we are passing here, because here we are supplying 2 moles of hydrogen, only 2 double bonds will undergo reduction. Okay, that means those 2 double bonds are from the first aromatic ring system. So upon saturation of 2 double bonds, so for the saturation of 2 double bonds, 2 moles of hydrogens will be consumed, and during this 4 hydrogens will be added at 1, 2, 3, 4 positions in the naphthalene ring system, and that is how we will be getting finally 1, 2, 3, 4 tetrahydronaphthalene as the product. This 1, 2, 3, 4 tetrahydronaphthalene is also known as tetralene. The other type of reduction is again catalytical reduction. So here when we pass 5 moles of hydrogen in the presence of platinum catalyst, all the 5 double bonds which are present in naphthalene structure will be hydrogenated. They will undergo reduction, and as a result of which we get completely saturated molecule, okay, which is nothing but decalene. So this is how, depending on the type of reducing agents or the catalyst or the temperature that we operate during reduction reaction, different types of reduced products will be formed from naphthalene. So from this, I hope the addition reactions, oxidation and reduction reactions of naphthalene are clear to you students. So if you have doubts, any doubts related to this topic, you can keep your questions in the chat. Alternatively, if you are watching the replay of this particular session, then a WhatsApp group link will be provided in the description. You can join in that WhatsApp group and you can also clarify your doubts at the later stage. Now, lastly, we are left with only structure and uses of naphthalene and its derivatives. Sometimes you are getting this as a 5 marks question. So let me share my screen to explain the same. Meanwhile, if you have any doubts, you can share, you can keep your questions in the chat. This is the structure of naphthalene, as you are aware. So naphthalene is used as insecticide and also it is used to prevent moths from cloths. Yes, students, you might have observed by this time, many of the families, even today also, they will be using naphthalene balls. They used to keep naphthalene balls in the cloths, okay, particularly whether it may be new cloths which we use for functions and parties, okay, and it can be woolen cloths, blankets, okay, and the uses of these naphthalene balls are most prominent during winters, okay. And not only for this, naphthalene is used in the synthesis of phthalic anhydride. We have seen in one of the oxidative reaction of naphthalene, we get phthalic anhydride as the product, okay. And this naphthalene is also used for the synthesis of several dyes and also medicines, okay. And the solution of naphthalene, it prevents rusting also. It is used as household fumigant against insects and it is used in the production of black smoke. Okay, generally army people or police people, they will be using black smoke, no, during strikes and all. So in that naphthalene will be used and also it is used to make or manufacture explosives. So these are some of the uses of naphthalene. Now coming to the naphthalene derivatives, so 1,4-naphthaquinone. I hope you remember this structure. So under ozonolysis, okay, ozonolysis of naphthalene and further hydrolysis, we will be getting 1,4-naphthaquinone as one of the product, okay, and also upon oxidation of naphthalene also, okay, we will be getting 1,4-naphthaquinone. So this 1,4-naphthaquinone is one of the derivative of naphthalene, okay. So this 1,4-naphthaquinone is also having antibacterial, antiviral and antifungal activity. Okay, and it is also used as insecticide. Now few more naphthalene derivatives are 1-naphthylamine and 2-naphthylamine. So here naphthalene ring systems are given and the 1-naphthylamine consists of amino functionality at first position, while 2-naphthylamine, as the name itself indicates, amino group will be present at second position. So 1-naphthylamine is used in the preparation of dyes. In fact, both naphthylamines, okay, all the naphthalene derivatives, they are usually used in the manufacturing of dyes, okay. Now, in addition to that, this 2-naphthylamine is used even in the rubber industry also. So I hope the structure and uses of naphthalene and its derivatives is clear to you. Okay, so you may get this as a 5 marks question also. So if you have any doubts related to the chemistry of naphthalene, that means so far whatever the topics that I covered in today's session, you can keep your doubts or questions related to today's session in the chat, students. So meanwhile, I'll share my screen to show you some of the examination point of view important questions. Meanwhile, let me show you some of the model questions when it comes to the chemistry of naphthalene. So the first question is define polynuclear aromatic hydrocarbons with examples. Okay. Write any two methods of preparation of naphthalene. This is for 5 marks. And write the structure and uses of naphthalene derivatives. As I mentioned earlier, this is also important. You may get as 2 marks question also. Write the structure and uses of naphthalene, direct naphthalene structure and uses, or structure and uses of naphthalene derivatives. Okay. So where I mentioned about naphthaquinone and all, no, that is 1-amino, 2-amino, alpha-naphthol, beta-naphthol. All these are the derivatives of naphthalene. Okay. So altogether you can write for 5 marks. Then explain the electrophilic substitution reactions of naphthalene. This can be asked for, so this question can be asked for 5 marks. And naphthalene, whole chemistry of naphthalene, that is naphthalene resonance structures, Haworth synthesis, any 3 reactions along with uses can be given for 10 marks. So these are the few important questions when it comes to the chemistry of naphthalene. So I'll stop here, students. So I hope the chemistry of naphthalene is clear to you from today's session. So if you have any doubts related to today's session, you can post your doubts in the chat. Alternatively, if you are watching the replay, then a WhatsApp group link will be available in the description. You can join in that WhatsApp group and also you can clarify your doubts at later stage. So soon after this particular session, quiz will be enabled, students. Okay. Review the concept after this session for about 10 to 15 minutes. Okay. Then attempt the quiz. Okay. Now in tomorrow's session, I'll be taking the chemistry of anthracene. Okay. So come prepare thorough with naphthalene so that you can easily understand anthracene, because we are going to discuss even the chemistry of anthracene under similar headings. Okay. So till then, take care. Let us meet in